Hello, and welcome to this presentation, Understanding Circulators and Isolators. In this presentation, we'll provide a short technical introduction to radio frequency circulators and isolators, including their basic function, their characteristics, and their common applications. We'll also briefly discuss how to measure or quantify circulators and isolators using test and measurement instruments. Circulators are often used as an alternative to filter-based duplexers. Although this presentation doesn't assume or require any familiarity with duplexers, please see the separate presentation, Understanding Duplexers, if you'd like to learn more about duplexers and how they're used. In many RF applications, the ability to control the direction or flow of RF power is very important. A good example of this is a system which uses an antenna. Here, we want power to flow towards or into the antenna, but if power is reflected from a mismatched or damaged antenna system, we generally don't want this power reaching the transmitter. A somewhat similar example is the case where a transceiver uses the same antenna for both transmitting and receiving. In this case, it's important to have a way to protect or isolate the sensitive receiver from the high-power transmitter. Duplexers, which are made using a combination of bandpass and band reject filters, are one way of creating this isolation. Another way is using a device called a circulator. So let's start by explaining what a circulator is and how it operates. Circulators are passive, that is, non-powered devices, usually with 3 ports as shown here. Although 4-port circulators do exist, they are much less common. In many cases, circulators are packaged with coaxial connectors, such as SMA or Type N, but there are also waveguide versions of circulators used in some applications, particularly radar. Recall from the previous slide that the function of a circulator is to direct and/or block the flow of RF energy in a given direction. We'll talk about this in much more detail over the next few slides. Note that circulators are generally non-tunable. That is, their frequency range cannot be easily adjusted. This is one of the main differences between circulators and filter-based duplexers. Note, too, that although circulators are passive devices, they are also not purely linear. This means that in addition to passing the input signal, circulators may also introduce additional signals, that is, harmonics and/or intermodulation products, so it's not uncommon to see low-pass filters placed on the output of a circulator in order to reduce the level of these undesired additional products. Now let's examine how a 3-port circulator routes signals. As the name implies, a circulator routes RF energy circularly between ports. Most circulators depict this rotation occurring clockwise. For example, signals input into port 1 are circulated forward in a clockwise direction to port 2. Similarly, a signal at the input of port 2 would be circulated clockwise to port 3. And a signal input at port 3 would be circulated clockwise to port 1. It should be mentioned that this last case, that is, an input signal at port 3, is somewhat uncommon in practice. The ports of a circulator may be labeled as input, output, and load, which alludes to how these ports are typically used. We'll talk more about this in just a few moments. Ideally, a circulator would introduce little to no attenuation or insertion loss in the forward direction, but would have high attenuation or isolation in the reverse direction. That is, signals would be routed unidirectionally clockwise, with no signals leaking in the counterclockwise direction. Circulators do this by using magnetic fields to route signals between ports, and thus circulators contain relatively strong permanent magnets, usually ferrite discs or triangles. In coaxial circulators, the signals are routed along strip line sandwiched between these magnets, with the ports spaced 120 degrees apart. Note that the center section of the strip line may be implemented in different shapes. Because they contain strong magnets, it's important not to place circulators too close to objects or devices that are either sensitive to the magnetic fields created by the circulator or to objects which might weaken or degauss the circulator's own magnetic field, since this could, in turn, degrade the performance of the circulator. Now let's come back to our two RF power routing scenarios. Recall that one of the most common applications for circulators is when an antenna is used simultaneously for both transmitting and receiving. Here, the circulator is used to separate a high-power transmitter from a sensitive receiver, and this is common in radar and two-way radio applications. And circulators can also be used more generically when we need to protect RF devices from reflected power caused by a poorly matched or damaged antenna system. In this case, the circulator is used to route the reflected power towards a dummy load or sink connected to port 3. We'll come back to this specific scenario in just a few moments. But first, let's look at the most important performance characteristics of a circulator. All circulators have a specified frequency range over which their maximum insertion loss and minimum isolation are specified. Recall that insertion loss refers to how much the signal is attenuated between a pair of ports in the forward direction. Ideally, this would be 0 and should always be less than 1 dB, with most coaxial circulators having between about 0.4 and 0.6 dB of loss. The isolation of a circulator is how much attenuation there is between a pair of ports in the reverse direction. Ideally, this would be infinite, but values from about 15 to about 50 dB are common. This is also influenced by the impedance match or VISWAR at the next port, with optimal isolation requiring a matched load. And finally, circulators will have a maximum power rating at which it will still deliver the specified performance. Going above this input power level may lead to degradation or even damage to the circulator. All of the circulators we've looked at so far are single stage, but it's also possible to construct a circulator with multiple cascaded stages. Usually this is only 2 stages, as shown here, but sometimes there may be 3 stages. All of these stages are, however, typically integrated into a single package. The reason for cascading multiple circulators is that this provides higher port-to-port isolation. This higher isolation does, however, come at a cost, namely higher insertion loss in the forward direction, greater size and weight of the device, and increased cost. Note too that most multi-stage circulators have the third or load port terminated. Terminating the third port of a circulator turns it into an isolator. This termination is usually in the form of an integrated 50 ohm load, which often appears as a small hump or disc where port 3 would be on a circulator. The reason this is called an isolator is that it isolates port 1 from port 2 in the reverse direction. As we showed earlier, this arrangement routes reflected power into the load on the third port and thus protects the transmitter. Note, however, that this small integrated load usually can only dissipate relatively small amounts of power, and thus isolators are only suitable for cases in which VISWAR or the level of reflected power are relatively low. If higher power must potentially be handled, then a circulator with a larger dummy load on port 3 should be used. Next, let's discuss how circulators and isolators are measured or characterized. Most often, a vector network analyzer is used, since these provide the highest accuracy and flexibility when measuring multi-port devices or networks. Note, however, that a spectrum analyzer with a tracking generator or with a broadband noise source can also be used. Even though circulators have 3 or more ports, in most cases, transmission measurements are only made between a pair of ports at a time, with the unused port or ports being terminated in their characteristic impedance, typically 50 ohms. And as we'll discuss in just a moment, the primary measurements made on circulators and isolators are the magnitude of the port-to-port insertion loss and isolation. Before we conclude this presentation, let's look at a measurement example. Here we see insertion loss, shown in red, and isolation, shown in blue. These correspond to S21 and S12 measurements, respectively. Looking across the nominal operating range of the circulator, 1.44 to 1.51 GHz, we can see that it has an insertion loss of less than 1 dB over this entire range. Isolation is 20 dB or greater over this range, and the maximum isolation, approximately 45 dB, occurs at about 1.475 GHz. Most circulators have traces similar to these, with insertion loss being relatively flat and isolation having a deep dip or notch towards the center of the operating band. Let's end with a brief summary. Circulators are passive devices which direct the flow of RF energy using magnetic fields. Energy entering one port is passed in a circular direction, typically clockwise, to the next port. There should be minimal attenuation or insertion loss in the forward path, but high isolation in the reverse direction. At least 15 to 20 dB is common. There are two main applications for circulators. One is allowing the use of a single antenna for both transmitting and receiving, and the second is protecting a transmitter or source from reflected power. In some cases, circulators are also connected in series or cascaded in order to increase isolation, but this will also increase the overall insertion loss. A common variant of the circulator is an isolator, which is simply a circulator with the third port terminated. And finally, vector network analyzers are the primary test and measurement instrument used to measure or characterize the performance of circulators and isolators. This concludes our presentation, Understanding Circulators and Isolators. If you'd like to learn more about RF components, how to measure RF components, or about test and measurement instruments from Rohde & Schwarz, please see the links in the video description. Thanks for watching. Please subscribe to our YouTube channel and visit us at rohde-schwarz.com.